Around 4.5 billion years ago, our solar system formed from a cloud of dust and gas. Earth was one of the planets that emerged. In its early years, Earth was a world of molten rock and dense clouds. But as it cooled, oceans formed, setting the stage for the first hints of life. About 3.8 billion years ago, life began to appear in oceans. Simple molecules joined together, forming the first single-celled organisms. These cells evolved into multicellular life, and eventually into the complex life forms we see today. This progression makes sense, because evolution favors organisms that adapt well to their environments. But one part is still a mystery. How did life start from non-life? In this video we will see that starting life might not actually require complex processes. Simple rules can lead to forms that closely resemble life. Look at those red particles. Their positions are random. When the simulation starts, they start pushing away from each other, so they are separated almost evenly. Let's try again, but now the particles will be attracting each other, but they will still push away if they get too close. Now they have formed groups. To create more complex behavior, we can add particles of different color. Now the particles of the same color are attracting each other. Particles with different colors don't yet interact with each other. Now the rules are the same, but the opposite colors repel each other. This leads to more separation between the colors. The forces between the particles are symmetrical, meaning that if yellow particles repel red particles, the red particles also repel yellow particles. But now the forces will become asymmetric. The red particles will be attracted to yellow particles, but the yellow particles will try to run away from the red particles. This already leads to a more complex behavior. After running the simulation for some time, the shapes that look like cells start to emerge. We can show the forces that are between the particles on a matrix. The top left cell means that red particles are attracted to red particles. The cell next to that means that red particles are also attracted to yellow particles. The bottom left corner cell has negative value. It means that yellow particles are running away from the red particles. The force between particles also depends on the distance between them. This is the graph of this force, where the x-axis is the distance between particles. Negative force means that particles are repelled, and positive means that particles are attracted. We can see that up to some small distance, all particles are repelled by each other. After this distance, the force is controlled by the force matrix. Now, we can just fill the matrix with random values and see what will happen then. Now, the simulation behaves differently. Looks like the red particles repel each other, meaning that the value in the matrix is negative. To see even more complex behavior, we can add another color. Now the force matrix is of size 3 by 3. Nothing stops us from adding another color. With just those simple rules, we can see a behavior that resembles real life. For comparison, these are real organisms under a microscope. Now, we can just make the simulation bigger. I rewrote the code so that it can run on the GPU. First, let's add more particles. With too many particles, we can see some shapes emerging, but most of it is just chaos. But we can also make the size of the simulation bigger. Now you are looking at 30,000 particles. This is 60,000 particles. It's hard to see the shapes because everything is so small, but we can make the max distance in which the particles will interact bigger. Now, the radius of interaction is 2 times bigger, so the particles should interact with more other particles at the same time. Let's go back to a smaller number of particles. And now I'm just gonna leave you with the best shapes I have seen emerge after running the simulation for tens of hours.